Hi everyone, welcome back to Intermediate Micro. Today we're continuing our discussion of production, and whereas last time we talked about the short run, now we're talking about production in the long run, which means all inputs are going to be variable. So one of the things to notice that when all inputs, in this case capital and labor, are variable, is we'll have different combinations of both capital and labor that net us the same output, the same amount of production. We see here that 1 unit of labor and 5 units of capital get us 75 output. Same with 2 units of labor and 3 units of capital, 75 units of output. Same with 3 and 2 and 5 and 1. And what we're describing from this exercise is all the various combinations of both capital and labor that generate the same level of output, in this case, 75 units. And we can put this information, these various combinations, on a curve. We'll call that curve an isoquant. Iso meaning same or equal, quant meaning quantity, of course, so same quantity. This curve shows all possible combinations of input that yield the same output. When we put a bunch of these curves on a graph together, we'll get an isoquant map, which is a graph combining a number of different isoquants, and we use this map to describe a production function. So this should sound very familiar to you. It should sound a lot like indifference curves and indifference maps in consumer theory, whereas in consumer theory, we're showing all the different inputs in goods and services that yield the same level of utility. Here we're showing all the combinations of labor and capital that yield the same output. And when we put all these isoquants on a map together, we see that they in fact look very similar to indifference curves, where output increases as we move from isoquant to isoquant, and mixes of inputs tend to put us on higher curves than extreme inputs. That's supposed to be a straight line, apologies. Isoquant maps afford us another unit of analysis, another level of analysis, which is we get to observe the law of diminishing returns in action. So in the short run, where we had a fixed input, we can fix an input by using just a straight horizontal line, here in the case of 3. So by fixing capital at 3 and drawing a horizontal line across, we can observe how different inputs of labor change our units of output. And from here we can observe the law of diminishing returns because one additional unit of labor is getting us less and less output as we move up the isoquants. From 1 to 2, the marginal product of labor is 20, moving from 75 to 55. But from 2 to 3, the marginal product of labor is 15, moving from 90 to 75. To say this a little bit more formally, isoquants are depicting two properties of production. One, which we just discussed, is diminishing marginal return, where even though we're now dealing with two variable inputs, it can be useful to ask what happens when one input is fixed, thus illustrating the law of diminishing marginal returns. The other property that it's useful to see with an isoquant map is input flexibility. Isoquants show us the flexibility that firms have when making production decisions, just the way indifference curves show us the flexibility that consumers have when making consumption decisions. Just like any number of chips and salsa can give you some level of utility, many different combinations of labor and capital can give you the same unit of output. And to keep that comparison going, Just how in consumer theory, the fact that we had different bundles which could provide us the same utility implying a marginal rate of substitution. In production, we also have substitution, in this case, substitution among inputs, which implies a marginal rate of technical substitution, MRTS. The marginal rate of technical substitution is the amount of capital needed to replace one unit of labor while keeping output the same. And isoquants typically display diminishing marginal rates of technical substitution as more and more labor is added. When a firm only has a small amount of labor, each worker is very productive, and so a lot of capital is needed to replace a worker and keep output constant. However, as the firm hires more and more workers, each worker is less productive, and so less capital is needed to replace that worker. What this looks like on an isoquant map is that downward sloping, bowed toward the origin isoquant for some output Q naught. What does this look like mathematically? Well, if the marginal rate of substitution is the change in capital input over the change in labor input, then we can derive a delta K over delta L term for a fixed level of Q to get our MRTS. This minus sign here is just because we've got these downward sloping curves. What does this amount to in practice? Well, we already have terms that look like delta K and delta L. Those are our marginal product of capital, which is delta Q over delta K, and marginal product of labor, which is delta Q over delta L. So in other words, and I'm going to clean up the slide real quick, marginal rate of technical substitution is just the marginal product of labor over the marginal product of capital. And I'll formalize that out real quick. So delta Q over delta L over delta Q over delta K. The delta Q's drop out. So we have 1 over delta L over 1 over delta K, or delta K over delta L, which is our MRTS term up here. I'm going to clean up the slide real quick, but graphically, what this means is that the MRTS is just the slope of the isoquant. This is a tangent curve. This is the isoquant for Q naught. Graphically, the MRTS, the marginal rate of technical substitution, is the slope of the isoquant. And again, as labor rises, put labor here on this x-axis, as labor rises, the marginal rate of technical substitution falls, and so the isoquant flattens. Here we have a numerical example just showing how similar isoquants are to indifference curves, where they tend to be downward sloping and convex. Convex means bowed towards the origin. And the slope at any given point of the isoquant is measuring that MRTS. In other words, it's measuring the ability of the firm to replace capital with labor while maintaining the same level of output. So let's take a minute and consider isoquant Q2, which is 75 units of output. As we add more and more and more labor, so 1 unit, 2 units, 3 units, 4 units, as we add more labor, the marginal rate of technical substitution falls from 2 to 1 to 2/3 to 1/3. Like I said on the last slide, it flattens as we add more labor. Take a minute to inspect this slide on your own and confirm that that's what's happening. And just like in consumer theory, how we had special types of utility functions that would give us specially shaped indifference curves, in production, we have special types of production functions that give us specially shaped isoquants. And they should look very similar to you. We have perfect substitutes. Just as we have substitutes in consumption, we can have substitutes in production. Maybe consider a firm that hires workers and also uses robots. Robots are capital, but they substitute workers quite well. We also have perfect complements in production. We might also call these fixed proportion productions or Leontief productions. This is much like perfect complements in consumption. So imagine a firm that has typists and typewriters. Typists can only use one typewriter at a time. A typewriter is useless without a typist in it. This firm is producing in fixed proportion or perfect complements. And we'll see in a few slides that just like in our consumer theory analog, we're going to have L-shaped isoquants, where only one combination of labor and capital can be used to produce each level of output. Why might such a production function exist in the naturally occurring world? Well, perhaps we have a situation where our modes of production are limited. Let's see what that looks like in practice. So isoquants with perfect substitutes are linear. They're downward sloping straight lines and look just like perfect substitutes indifference curves in consumer theory. In this case, one additional unit of capital always adds the same amount of output as one additional unit of labor. Last slide, we gave the example of laborers and robots as perfect substitutes for one another. Take a minute on your own to try and think of other firms you might know that might have perfect substitute-like inputs. Noting that since perfect substitutes have linear isoquants, the MRTS, the slope of that isoquant, is constant. We also spoke about fixed proportion production functions, also known as perfect complements in production or Leontief production. Mathematically, these look like a min function, the minimum of labor and capital, and what a production function that is in fixed proportion implies is limited modes of process. The fixed proportion production function describes a situation in which the methods of production are limited. So the example I gave a few slides ago of typists and typewriters. And we can see here, and I'll switch the color up, that if, say, we're at point A, adding more capital, adding more typewriters, doesn't get us any additional production. And if we're at point A, adding more typists doesn't get us any additional production. We're still at Q1. But if we add a typist and a typewriter in a fixed proportion, we get up to Q2, and adding more gets us up to Q3. But suppose we're at point C, adding additional typewriters doesn't get us any additional typing. We went through that pretty quickly because by now you should be reasonably familiar with how these curves work in practice. But let's see these isoquants in action, in this case with an example for the production of wheat. Wheat is interesting because it's something that human beings have produced for a very long time, and over time, the extent to which we've used capital to produce wheat has changed. Right now, with commercial farming in the US, wheat is usually very capital intensive, meaning it uses a lot of machinery to farm and not that many people. But you can imagine a world, either now or in the distant past, where you had many, many people working on a farm without very much machinery. In the US, labor tends to be more expensive than machines, more expensive than capital. This isn't true on wheat farms in the developing world, where labor is cheap and capital is very expensive. Let's see if we can describe this trade-off and this dichotomy using an isoquant map. So here we see an isoquant associated with a little less than 14,000 bushels of wheat per year. And if you are a farm manager, you can use such a mapping, such an isoquant, to decide whether it's more profitable to hire labor or use machinery. And the exact labor to capital combination you pick will depend on input prices, a subject that your book discusses in Chapter 7 is out of our scope for this semester. But what we see is, at point A, a much more capital-intensive process, where we're using 100 units of capital, and it has a relatively steep MRTS. And at point B, a relatively labor-intensive process, where we're using 90 units of capital, 760 workers, and a much more flat MRTS. In other words, though different inputs provide the same level of output, point A is much more similar to the US or Canada, and point B is much more similar to the developing world. As we jump from isoquant to isoquant, we can describe the rate at which output increases in response to proportionate input increases. And we can describe this qualitatively. You might remember this from your 101 class as returns to scale. So we have increasing returns to scale, where if we double all our inputs, our output will more than double. We have constant returns to scale, where when we double all our inputs, output also doubles. And we have decreasing returns to scale, where when we double all our inputs, output will less than double. Now we're going to have a reading, and I'll post it in the link below, the description below, of why decreasing returns to scale don't really exist. But because we can abstract, because we can hypothesize, let's take a minute to think about what these cases might look like, what increasing, constant, and decreasing returns to scale might look like. So while you're thinking of potential examples, think about firms you know, industries you know, and also think about history you might know. So in the case of increasing returns to scale, where we double all our input and output more than doubles, output greater than 2x, we can famously think of the automobile industry, and the automobile industry specifically with the introduction of the assembly line, where not only did we increase our workers, but by specializing our workers, Capital didn't change, but output was changing by more than that input. For the most part in econ, we tend to think of a space where we're at constant returns to scale, sort of a steady state. And here we might think of your typical office job, where small offices have a small office space and a small number of employees and are able to serve a small number of clients. Large offices have a lot of office space and a large number of employees and are able to serve a large number of clients. But those ratios tend to work in constant return. So I started this slide by saying decreasing returns to scale tend to not really exist. And we're going to have a reading to describe why, but take a minute to think about it on your own. What decreasing returns to scale means, when you double all your inputs and output less than doubles, is someone somewhere is fouling up. It means you have a coordination problem or difficulty maintaining a useful line of communication between management and workers, or difficulty maintaining your task. And in those cases, we tend to think that the market will beat those businesses out. Those firms will tend to lose over time and eventually go out of business. We can explore these conceptual relationships graphically and note that returns to scale don't need to be uniform across all possible levels of output. For example, at lower levels of output, a firm could have increasing returns to scale as it ramps up, but eventually when it gets to size, it will be constant. And if the firm grows too big for its britches, as it were, it might experience decreasing returns at these high levels of output. In figure A, what we see here is the firm experiencing constant returns to scale. To go from a unit, from 10 units of output to 20 units of output, we need to double our labor and double our capital. You'll notice that the isoquants are evenly spaced because output is increasing proportionally. Similarly, starting from our initial isoquant of 10 units to get to 30, so to increase our output 3 times, our input needs to increase 3 times. 5 times 3 is 15. 2 times 3 is 6. 10 times 3 is 30. Sometimes, however, we might be in a situation where the firm is ramping up, where we have increasing returns to scale. We can double our output, in this case from 10 to 20, with less than a doubling of the input. So here's some number, let's call it 7, doesn't have to be, but we'll see that it's less than 10. What this looks like graphically, what increasing returns to scale looks like graphically, is our isoquants getting closer and closer together. See how the jump from 10 to 20 is spaced further apart than the jump from 20 to 30. So we'll close today's lecture with an example of what returns to scale look like in the carpet industry. Carpeting is a really capital-intensive production process. And over time, the major carpet manufacturers have increased the scale of their operations by putting larger and more efficient machines into larger plants. When you go on to take urban economics, you're going to see that a lot of the carpet industry is all located in a similar space, North Georgia. What have these carpet manufacturers seen as a result of their changing labor and capital practices? Well, smaller manufacturers have found that small changes in scale have had little to no effect on output, whereas large manufacturers who are able to afford these big machines have found that small changes in scale have relatively large impact on output. So the carpet industry looks like one where there's constant returns to scale in small plants and increasing returns to scale in large plants. And as a result, we see relatively fewer and fewer carpet producers, and those small number of carpet producers, mostly located in Dahlonega, Georgia, those small number of producers operating very, very large plants. Take a minute to think about what you know about production and convince yourself why this might be the case, and maybe come up with a counterexample if you can. That's all we have for today. Look forward to talking with you all next time when we introduce game theory.